I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science and engineering. My name is Taylor Sparks. I'm a professor of material science and engineering at the University of Utah, and I am joined once again by Andrew. Andrew, how you been?
Yeah, it's been quite a while. I'm out in Maryland. Well, I'm actually in Virginia, but my internship is in Maryland, and it's been an experience. The traffic out here is pretty much next level compared to Salt Lake City, and I knew it was going to be bad, but I didn't quite understand what I was in for, and so it's been a bit brutal. In order to get to work in a reasonable amount of time, I hate being in traffic. I'm very much, when it comes to commuting, a destination person. Like, it's not about the journey at all for me. So I wake up like at 5:30 so I can try to get to work before 7, because anytime later it's like exponential in terms of the amount of time you're going to have to wait. And the Maryland drivers in particular, sorry to any fans from Maryland.
There go all of our Maryland fans.
Yeah, if you use, well, there's those exit and on ramps on the highways.
Yep.
They'll just pull onto those and skirt above the, try to get around traffic and then just try to wedge themselves right back in. It's like, this is why we are stuck here in traffic, because everyone has to keep waiting while you try to, cheat your way around it.
It's a zipper, people. You just got to zip.
Yeah, but not everyone's there. So, but it's been good. I haven't been out east in a long time. I was born in this area, but it's been nice to return to my roots in some sense.
Well, that's awesome.
But how's your summer going? How's Utah?
It's fantastic. Yeah, everything is great. We were wishing you here, but we're excited to have you back at the end of the summer, man.
Yeah, is it as hot out there as it is here?
It is 1 billion degrees. It is the surface of the sun, but 15% humidity, max, instead of wherever you're at, where I'm guessing it's close to 80-90%.
No, not quite. Up in my area, it only gets to about maybe like 50% at the worst.
Manageable.
Which is actually quite good. I thought I would hate it more, but my skin is liking it. For like the first time, my skin actually is like not dry for once. So it's been a blessing in that regard.
Well,
but we have a really exciting episode today.
We do. People have asked and asked and asked for this one, and we're delivering. Okay, so before we get started, in this episode, we're going to talk about materials that are made by combining a bunch of different elements. So it only makes sense to recognize our sponsor for today's episode. And this episode is brought to you by American Elements, the world's manufacturer of advanced materials. AmericanElements.com. Now invent. This is a field that has revived a field that was kind of going, not dead, but it was really a little bit, I've been to some of these metallurgy conferences and they were a little bit sleepy. And then this field showed up about 20 years ago and just turned it on its head. So why and how? First off, you're getting absolutely bonkers properties out of this new class of materials. And I mean it. Fracture toughness is between, say, 200 and over 400. I grant it at crazy temperatures, right? But still, put that in perspective, right? Tough steels, 50 to 100 megapascal root meters, that's already like really impressive stuff. And all of a sudden, you're telling me that we could go to several hundred? Like, that is wild. But it's not just toughness. We're seeing really cool performance when it comes to strength, to wear resistance, corrosion resistance, irradiation. So what is this magical new class of materials, Andrew?
So the popular name for this is high-entropy alloys, although that itself can be a little bit of a misnomer. But the people who invented this field, that was the term that they gave it.
Yeah, when you show up first, I guess you get naming rights.
Yeah, of course. I mean, it's the same thing with like SPS, right? The spark plasma aspect isn't really totally there from a theoretical perspective, but everyone still calls it SPS. And if you look in the literature, HEA still is the dominant term as well.
Oh yeah, for sure. And honestly, the discovery is really a great place to start because it's fascinating. The person who gets all the credit for this is Brian Cantor. In fact, somebody, I don't know how it became named, but the Cantor alloy, right, is the family that he was working on in this first paper. He's at Oxford in material science and engineering. Although the corresponding author on that paper was actually a guy I.T.H. Chang at Birmingham, who doesn't get as much credit here, but I think probably deserves a fair bit. They published their paper, this landmark paper, which kicked off the field of high-entropy alloys in December 31st, 2003. There was another paper, and it was one of these cases where, God, this happens so often in science, where there was like serendipitously an independent parallel discovery, right? This paper was actually submitted online December 1st, so 30 days before. So it's not like they saw the preprint and hurried and got something out. Like, it was technically out before they could have seen it. So this 30 days before, this is out of National Tsinghua University in Taiwan. This is by Jianwei Ye and co-workers. And these two papers are super duper similar. Brian Cantor and his team, they worked in this family. Well, they tried a whole bunch of things. And the whole premise of what they were trying to do is by mixing a bunch of different metals together in equal amounts, equiatomic ratios. So they tried mixing, if you believe it, 20 different alloys together in a single alloy, right? 20 different elements in a single alloy, which is wild. And those were terrible. They tried 16, and those were terrible. But as they lowered the number down, they found that actually 5 constituents, iron, manganese, chromium, cobalt, and nickel, actually worked. And also they tried the 6 to 9 components. They also worked. And what was absolutely shocking, and was the real report of their paper, it's kind of where they spent their time, is that it had a single FCC phase. So we'll talk in a moment about why that is so completely shocking, but that was very surprising that you get a single phase. Those things should not be solid soluble one with another. So the other paper, go ahead.
Yeah, I was going to say, that's pretty counterintuitive, right? With most alloy design, or even if you look at a phase diagram, typically you're going to stay near the boundaries, because that's where you're going to find those sorts of solid solutions or the intermetallics that you might be desiring. In towards the middle of your phase diagram, especially when you get into such a high dimensional space, the odds of you finding instead like a intermetallic or some sort of secondary or tertiary phases that are going to form would seem, and I think the main sort of thinking at the time was that that's what would emerge. But that wasn't what happened.
Oh, absolutely. And that's why it was so shocking. Consider steel, for example. Steel is, obviously, we know it's iron and carbon, but how much? It's like overwhelmingly iron. It is a very small amount of carbon. By weight percent, you're talking less than 2 or 3%, right? Unless you're even like your cast irons are up to maybe 4%. Like, it is not very much. And when they add other components, manganese, chromium, nickel, like stainless steel, that's kind of an outlier because you're adding between 10 and 15% nickel and then about the same amount of chromium. Still, you're at the corners of the phase diagram. And here, they're intentionally, by design, putting it directly in the center. They want equiatomic ratios. So the fact that they're going to find something that's a single phase there was shocking. Because think Gibbs phase rule. Let's rewind to Intro to Material Science. You've seen phase diagrams. You remember Gibbs phase rule. P plus F equals C plus N, right? So P is the number of phases that can exist in thermodynamic equilibrium. F is your degrees of freedom. So let's bring that down to 0. So we're at like the triple point, as it were. And then on the other side, you've got C, the number of components, and N, the number of non-compositional variables. So if we only consider temperature for a minute, then you still, if you have 5 different alloys, 5 different elements coming together in your alloy, you have on the right-hand side of the equation 6, and on the left hand, you've got P plus 0 equals 6. You could have up to 6 different phases in equilibrium, which is why it was so shocking, right, that they found just the one. Now, the other group out of Tsinghua, ironically enough, they ended up working on almost the exact same alloy system. There was only the difference in that instead of manganese, they had copper. Otherwise, it was the exact same system. So theirs was iron, copper, chromium, cobalt, nickel. And then they did something interesting that the Cantor group didn't do in their first paper. They slowly added a small amount of aluminum from 0 up to 3%. And they found that when they did that, there was this smooth transition from FCC, which is the phase that the Cantor team saw, to a mixture of FCC and BCC, and then eventually to a BCC phase, over 2%, 2.5% it was BCC, under 0.6 it was pure FCC. And with that change in phase, they saw a smooth transition in hardness from about 100 Vickers hardness up to 700. So all of a sudden, all bets are off. This is a really exciting area to work in because it looks like, holy smokes, it turns everything on its head. Like, we can discover alloys that we never would have considered would be single phase before, and therefore, what else is out there? And will they also have such cool properties, like actually really quite good hardness values?
Yeah, absolutely. And I think if you're a professor or a grad student, all of a sudden, like, all bets are off. Like, there's a huge, vast amount of space to now explore as well, and plenty of opportunity for new papers in this area, as well as a lot of low-hanging fruit that people thought just wasn't there, but maybe more interestingly, a lot of potential as well. You open up this vast composition space that can now be explored near the center of these many component systems and their phase diagrams, and all of a sudden it's like, well, what else is out there that hasn't been discovered? Right here we now have a new haystack of potential materials that we can sample, and the chances of finding a needle in that are, well, not zero.
So the floodgates are open, and you can see it at these big conferences. HEAs are big. Funding in this area, papers in this area. There's a lot of excitement, and this, I'm sure, will be only the first of a couple episodes on it, because we're going to talk about alloys today, but there's likely that we're going to talk about high-entropy ceramics and other things in the future. So when we talk about high-entropy alloys, if you've heard about them, you've probably heard it in the context of the so-called four-core effects. And these are the following: that you have the entropy effect, that you have the sluggish diffusion, that you have lattice distortion, and then the so-called cocktail effect. And we're going to go through these one by one and talk about them, because there's, at least it's not as straightforward as it's been cast, that anytime you H&A, that these things are all definitely happening and definitely driving the properties that we observe. In fact, there's been some papers out there that have kind of challenged some of these assertions. So let's dive into it. They call these things high-entropy alloys. Where does that term come from? It's coming from configurational entropy, right? So think way back. You saw this at some point. If you haven't, configurations is like the number of configurations that have the same energy, right? So the classic example is like parking spots, right? If there's like a parking lot that's empty and you put one car, right? That car could be in any one of those spots, and imagine that's equal energy. But then as you put two cars in there, that changes the number of permutations, and 3 it changes, right? So you can actually calculate this configurational entropy. It's pretty straightforward. It's just the gas constant multiplied by the sum of the fraction times the natural log of the fraction of each individual component. So it's actually a pretty straightforward calculation. And if you're doing like the Cantor and the Ye teams, where you had equiatomic ratios and there was 5 different components, you do the configurational entropy calculation and it comes out to 1.6 R. So that's pretty high compared to traditional alloys, right? If you compare this to something like a normal, like a conventional alloy, like a brass or a bronze, those things have less than 1 R configurational entropy. And then if you were to move to like a stainless steel, which again has like, 10 to 15% of that chromium and nickel that's adding quite a bit, maybe you'd have sort of medium entropy alloys where it's maybe 1 to 1.5 R. But now when you do this equal amounts of so many different ones, like 5, you're getting over 1.5. And so those are typically deemed high entropy as opposed to medium or low entropy.
Yeah, and this is also where the idea of a single phase emerging came from. And this was kind of some of the initial thinking as well, is if you can max out this entropic term, then it's possible you can overcome the enthalpies of forming different phases. And that might be what stabilizes a solid solution with so many different chemical components.
Yeah, think back to if you've had thermo yet. If you haven't, when you want to, in the universe, right? Thermodynamics says what happens. Gibbs free energy is the convenient term for doing that, the convenient energy term for doing that. And it is made up of an enthalpy, a bonding term, right? It's related to bonding, and an entropy term, right? And so from an entropy perspective, the system gets lowered when you mix things. So a solid solution, like a perfect mixture of 5 different atoms in some sort of arrangement, say like an FCC lattice, that makes a lot of sense. Entropy is favoring that because now you've got all this disorder. But why that normally doesn't happen is exactly what you said. You have this enthalpy of formation, right? The enthalpy term, you actually get pretty significant lowering of the energy by forming bonds, right? In intermetallics. So if you normally would, and this is why it's so shocking, when you take 5 different elements, you would assume that some sort of intermetallic would form, like a nickel aluminide or a, whatever. There's these really quite energetically stable intermetallic binaries that should be forming, which would give you a mixture of phases, which usually is garbage for alloys. And here, the fact that they didn't, that's why people started to postulate, well, maybe the reason that it didn't is because that entropy term was just so big, because the configurational entropy is, at least like maybe like 1.5 times bigger than normal, maybe even double this conventional alloy.
Yeah, and I think a lot of that analysis ended up emerging from that Cantor ally, where alloy where it's stabilized as an FCC. But some meta-analyses that have come about in review articles have kind of taken a look at this claim of thinking, well, if we just add a bunch of elements, is this really just always going to result in a solid solution? And it turns out when you
Nope.
survey the literature that the overwhelming majority of them actually result in 2 or more phases when they're mixed. And so it turned out to be that the enthalpy terms are actually more significant than you might think for a lot of these intermetallics or other phases. You'll get things like spinodal decomposition as well, or that there are other entropic terms as well, like vibrational entropy, that can also
Right.
that could be in a much greater magnitude than the configurational entropy and kind of affect what results. But the bigger thing was, as we kind of mentioned, was even if it is resulting in multiple phases, most of our high-performing alloys have multiple phases as well.
Right.
So even if we're
Steel.
not getting, even
Nickel
if we're not,
superalloys. You guys have heard our episodes.
even if we're not getting the single phase that was initially quite interesting from a scientific perspectives, there's still a lot of use here. And so that led to some additional terminology emerging. You'll see in some articles or talking to some experts, instead of using the term high entropy alloy, they'll use things like multi-principal element alloy, meaning that there are several elements that have a substantial fraction.
Or compositionally complex.
Yes, CCAs. And I think there's another term that some people will use. And the distinction's quite nuanced. And I think the review article, I think it was in 2017, by Miracle and Senkov, gives a really good distinction between them, where they classify them as high entropy alloys being alloys that are seeking to maximize configurational entropy, targeting a single phase formation.
Right.
Whereas multi-principal or CCAs being, compositionally complex alloys that have a lot of principal elements. And that makes a lot of sense, I think.
But maybe it doesn't have a single phase, and maybe that doesn't even need to, is kind of what they're saying in those ones.
Yeah, I think so.
That said, I think this is just really wild because, again, our audience, I think, is a lot of like introductory material science students, and you just learned in your intro course like rules for solid substitution. Like, there's a reason why most phase diagrams, if you look at a binary, that the regions where there's solid solubility are quite small because you have to have these so-called, these Hume-Rothery rules. Hume-Rothery, by the way, amazing guide. I was reading about him. A virus made him deaf when he was 18, and he still went on to have like this epic legacy career. Like, so cool. Anyways, he was also at Oxford, died in like the 60s, so I don't know if he overlaps with Cantor. Probably didn't know him, but how cool. But Hume-Rothery, he had these 5 rules. He said, like, okay, if you want to substitute a metal atom in for another one and keep solid solubility, you have to have 4 criteria. The first one is that the size of these things has to be about less than 15%. If it's way bigger or way smaller, it's not going to be a substitution. The other one is that it should have the same valency. If your copper's 2+, your nickel should be 2+, right? They should have the similar electronegativity, and we know why that on that one. If it's a big difference in electronegativity, it's more likely to form an ionic intermetallic bond or something. So you'd like it to be close to the same. And then lastly, they should have the same crystal structure. That only makes sense. If you've got FCC on one side of the phasogram and BCC on the other, you're clearly going to have a gap in the middle where they don't have the same structure. You're going to have a mixture of the two. And then basically the same rules exist for interstitial, but now it needs to be much, much smaller than the host, and then the same sort of criteria. And here, if you look at the 5, that they sort of had, they completely break that rule. Like, you would have never expected this to be single phase. So if nothing else, this is challenging old guidelines and old rules, and maybe there's new science to be discovered. It was kind of the idea here.
Second of these effects is this idea of sluggish diffusion. And if you think about it, it kind of has there's some intuition there, right? If you have all of these different elements of different sizes right next to each other, it's going to be pretty cramped, and it's going to be pretty difficult for elements to move past one another, for their atoms to move past one another and diffuse properly. This was thought to be an effect in a lot of papers early on. We're citing this as one of the properties of high entropy alloys. But a number of analyses have come out, especially in recent years, that have challenged this quite a bit, showing that many of the alloys that are pointed to for showing this sluggish diffusion are high in manganese to a statistically significant margin. And it would seem that it's actually the presence of manganese that causes many of these to exhibit that. But when you look at the broader class of HEA literature that has been published, in many cases, the diffusion, though maybe a bit slower, like it's not fast by any means, but it's not any slower than a conventional alloy.
Yeah. Like, honestly, it was a good hypothesis, right? And that's kind of the point that I I like the St. Coffee Miracle paper. They point out that these 4 so-called core effects, it's better to think of them as hypotheses. Like, these are good possible solutions, but we should test them and confirm them. And they basically point out, like, look, yeah, it could be that by having 5 different alloys on these different, equal sites because they're in one structure, that one site might technically be lower in energy, and therefore an ion that sits on that site could feel trapped. It could have slower kinetics. It's a good hypothesis, but, science is all about testing and proving or disproving those things.
Yeah, and I think the HEA community is a good example of this because it's pretty rare to see, or well, not rare. It's nice to have such a recent discovery or almost paradigm shift in terms of where the scientific community is directed, especially in the alloy space, where we can see the emergence and either acceptance or disapproval of various hypotheses that emerged early on, because this was only in the early 2000s that these really came about and rose to prominence.
Yeah. So the next of the 4 core effects, the third one, is lattice distortion. And again, you've probably seen, like, instead of this nice perfect cubic FCC lattice, when you see them talk about this, they'll show you a super rickety structure where some are too big and some are too small. And so instead of being nice and uniform, it's a highly distorted lattice. And from a hypothesis standpoint, that makes sense. The problem is actually measuring and confirming that has been tricky. It's been hard to actually prove that that's the case. And the tools that are available to us are hard to actually show this level of distortion. And even if it's there, for sure tying it to the properties which you would expect from that. So for example, one of the things that's often pointed to is these are really strong alloys. They do have remarkably high strength in a lot of ways. And so people are like, oh, well, that's solid solution strengthening, right? A dislocation, is getting pinned by the strain fields from a distorted lattice, basically. And so they're feeling that slowing of their ability to move through the lattice, and maybe that's responsible. But that's not been definitively ruled as the possible, because there's other things that could be playing a role here.
Yeah, and getting measurements of that is also very tricky. And I think if some of the other literature, or if the HEA literature is any guide to go by, it's definitely possible that there's quite a bit of variation across the HEAs, in the sense of you might be able to observe this in some,
Yeah,
but not
that's
in
right.
others.
Yep.
And so, it's difficult, I think, for many researchers to find the motivation and probably the funding to actually go through with those, because I'm pretty sure you need a synchrotron to do it.
Well, that's the thing. Look, let's say you're like, oh, we're going to do synchrotron. The problem with diffraction is that it is a long-range order measurement. It measures long-range order. To get near neighbor, yes, you can do like PDF, you can do, diffuse scattering, but it's hard. There's things like NMR, there's tools out there. You could try and visualize it directly, but it is not straightforward to capture the type of distortions that they're talking about. So no wonder that it's hard to pin it down and say exactly whether it's the origin of some of this behavior or not.
Yeah, one of the last effects is a little more philosophical, as opposed to some sort of mechanism, and that's the idea of the cocktail effect.
Yeah, less of a hypothesis on this one.
Yeah. The idea basically being that the sum of these many individual parts is greater and more unique than any of them individually. That meaning, you could add 2 elements together and they could produce effect that may not be suggested by them. For example, maybe 2 weaker alloys, when added, have a dramatic improvement in the strength, which you wouldn't have suggested based on the properties of each element alone. And so the idea is that with so much compositional complexity, the potential for emergent effects or surprising effects to emerge seems quite a bit higher. And philosophically, this makes a lot of sense. With that many degrees of freedom in terms of your composition and the ability to add a lot of elements that can interact in very complicated ways, the ability for just bizarre behavior, or at least unusual behavior, to emerge seems probable. So we've talked about the 4 effects that typically characterize these. But the question is, with all this chemical complexity, how do we now organize this space? Right? Like typically for steels, right? Well, we know the components of steels, and so the family typically will just include other additions to that. But with multiple principal elements, it starts to become a little bit tricky. You can't just base it off 1, 2, or maybe even 3 elements that are present, because a lot of them are going to share that. And thankfully, a number of families have emerged, but there tend to be very soft boundaries between them.
For sure. That said, the original, right, the OG HEAs, That's going to be your top row of the transition metals. That's your guys like titanium, vanadium, chromium, manganese, iron, copper, nickel, the guys that showed up in the Cantor alloy, those things. That's your sort of OG ones. But it didn't take long before people started to say, like, well, shoot, if we're getting such amazing properties there, and if it's so interesting and fundable and people are reading these papers, let's try it with all sorts of other stuff. So you started thinking about light weighting, and they said, okay, maybe not just a lithium alloy. And what's kind of funny is they've already kind of been doing this. Like they've been adding lithium to aluminum alloys, for example, for lightweighting for a while, right? I've been writing homework questions on this for 10 years. But then you've got magnesium, you've got beryllium, like you've got a space to explore there. The same could be said for refractory HEAs. And these are actually really interesting because in the refractory HEA world, now you're looking at things like zirconium, niobium, tungsten, hafnium, tantalum, tungsten. Those all are high melting point things. So now you can start thinking about, okay, it's an HEA, but it's a crazy high melting point one. And I've seen some work on that for, thinking about if we're ever going to replace nickel superalloys, which we know and love, maybe that's something. I know certainly the ARPA-E, when they funded a couple dozen teams, several of them were aiming at HEAs, these refractory HEAs in that area.
Yeah, and I think one of the, the potential hopeful things is one of the big problems with a lot of the refractories is that they're just very brittle. And so one thought is that, well, if some of these, transition metal HEAs can show pretty remarkable ductility, as well as high toughness and damage resistance, well, here we might have an opportunity and a potential path forward. And I think we'll maybe get into it a little bit later in the show, but there are quite a few really promising HEAs that have emerged from the refractory family. There's also quite a bit of work, and this is more of a scientific curiosity, looking at lanthanide HEAs. This is with elements like dysprosium, gadolinium, lutetium, terbium, thulium, the sort of elements that you don't really encounter on a daily basis, things like yttrium as well. And as you can imagine, these are pretty expensive to make, but there's a lot of interest in forming solid solutions from them, and in using them and using these really complex interactions that they bring about, it's possible that there could be some interesting mechanistic understanding that comes from them.
No, man, you know what this was? This was big rare earths. They were tired of separating those things. It's too hard. So there's like, no, here's what we're going to do. High entropy lanthanides. No separations necessary. Brilliant marketing, big rare earth. Well, my hat is off to you.
Yeah, there you go. The earth has already mixed them well enough.
And then, the last thing, well, I guess there's precious metals, right? You can mix together gold, ruthenium, rhodium, platinum, palladium, right? And maybe get interesting performance. Those are oftentimes used in catalysis. And so I'm actually not aware, maybe that's a future episode to think about HEA. Do you see a benefit from the entropic or any other aspect of these in catalysis? I don't know. That's maybe an interesting area. But I did find something that's kind of interesting, that now people are thinking about interstitials as being high entropy. So in other words, don't just use carbon to fill up the interstitials between a lattice, but maybe you have a mixture of carbon and silicon and boron and nitrogen, oxygen, right? Whatever these things that can form interstitials, that's kind of an interesting idea as well.
Yeah, good luck ever recycling these things.
Oh gosh.
You could make them even more high entropy.
Yeah.
But I think one of the kind of interesting things about these families, and there was a great article that tried to map where these families sit relative to conventional articles, and they point out kind of something interesting, that within the conventional alloys, like your aluminums, titaniums, steels, there's often a lot of gaps in terms of their strength versus density, or maybe their yield modulus. And these gaps were kind of difficult to fill, and many applications just had to say, well, we have to design to be on one side of this gap. But now these tend to blend and fill in those gaps while offering pretty similar performances. And so now the ability to customize alloys to very specific applications or needs has emerged in a really profound way.
Yeah, I mean, think about it. You have the biggest compositional space yet, like absolutely colossal compositional space, and we're seeing different enough properties that tailored alloys really starts to be a possibility if, and this is a big if we can learn how to traverse this massively high dimensional space in an efficient way. And there's people trying to do this. I mean, the leader of the pack, in my opinion, is Raimundo Arellave down at Texas A&M. They're doing really cool stuff in this area. They're building cool visualization tools. They're building really cool modeling and Bayesian approaches to sample that space. So fingers crossed. That said, I really like the Miracle Sankoff paper. This was, again, back in, I think, 2017. And they're like, hey, this field's been around for 12 years and it was really hyped. And yet we've only got like 7 alloys. One would have expected, a more auspicious number of alloys given the opportunity, the space, the emergent properties, and yet we don't have that many commercialized yet. So still work to be done.
Yeah, and I think a lot of the points are, well, there's a couple challenges here, right? These commercial alloys have a pretty big industry behind them, and
Yeah.
they're going to be cheaper just because of economies of scale. People know
Yeah.
how to produce them. They've been
And think
dialed in over centuries.
Iron is dirt cheap. Now you're going to replace that with something that has equal amounts of nickel, cobalt, chromium. Like those are all expensive. Stainless steel is expensive because the chromium and the nickel that go into it. Now you're going to like make the whole alloy out of these expensive things. It's got to have some, even if it does have some impressive properties, it may not be good enough.
Yeah, it's going to be really challenging to do that. And I think another hiccup, and a number of articles have pointed this out, is trying to make these and test them, right? The space is quite large. To try to do high throughput methods would suggest themselves to be quite good here, but high throughput usually doesn't measure the properties that are actually of interest, especially for the people who are going to be using these in structural applications, right? It's pretty quick and fast to arc melt, a bunch of these HEA samples and do micro hardness testing, for instance, but that doesn't necessarily tell you about its tensile yield strength, which is or other sorts of
let alone other properties, magnetism or whatever else. Like these are hard to measure on a compositionally graded, film or whatever.
Yeah, and I mean, the bulk properties are also going to be quite different, right? A lot of these are let cool. There's quite a bit of work now, and I think the field is definitely shifting towards putting a lot more effort into processing and exploring the effects of that to try to isolate the phase. But if you just cast this, or even if you don't apply any proper heat treatment, you're just going to get, whatever equilibrium phases are going to emerge. And so some have pointed out that the properties that are reported are probably towards the lower end of what each of these alloys can achieve.
Yeah,
and so
I think that's reasonable.
The composition space is quite vast, but now pair that with an equally probably vast property space, and it starts to become a little bit unwieldy in terms of how you traverse this.
Which is why you're starting to see modeling efforts really grow up. Like I've seen dozens and dozens and dozens of ML papers where they're predicting which phase will form when you mix together different HEAs. Will it be a single phase or a mixture of phases? If it's a single phase, is it BCC or is it FCC? Right? I've seen tons, and they've been fairly low quality, if I'm honest with you, a lot of these papers, but the trend is getting better, and it is an important question to answer, and it is surprising. Like, look, we're already turning Hume-Rothery rules on their heads, so it's not surprising that it's going to be a hard thing to learn, and the data-driven approaches are certainly one approach, but also at the same time, I'm hoping that we can get some new mechanistic insights on why different phases form. I haven't seen that yet.
Yeah, and you had mentioned Dr. Roive at A&M, and I had the privilege of working under him through an REU back in 2018. It's a long time ago.
You guys were doing shape memory alloys, or was it HEAs?
No, we were looking at corrosion at the time.
Oh.
Excuse me. Yeah, we were looking at HEAs and looking at the oxides that would form under high temperature applications. But he gave a really good talk at TMS in like 2021, I want to say, basically saying that the HEA space isn't really as big as we think it is.
Yeah, I've heard that talk.
And this isn't to say that the composition space isn't vast, but rather once you start applying practical constraints in terms of what an alloy needs to be commercially accepted, that is certain melting properties, phase stability, the ability to machine it or cold work it or things like that, all of a sudden, what was a vast space of maybe 1 million potential compounds comes down pretty quickly to maybe 1% of that or 4%. Yeah. Now that's, he mentions
still pretty awesome.
1% of a big number is still a big number. But we have to be wary of a number of the constraints that exist here when we try to make something actual. So maybe the next question is, how do you actually go about making these? Yeah. We mentioned arc melting, and that's a good way to do it. A lot of these elements that you're mixing together are going to be probably sensitive to oxygen, especially these refractory ones. Like you have zirconium and titanium in there, like one of the some of the most sensitive elements.
We use them as oxygen getters.
Yeah.
It's going to make it hard.
So being able to pull that's going to be absolutely essential. And just to make a callback, one of the big problems is you're trying to mix all these together and get them homogeneous. Kind of hard to do, getting metal powder, which is often flammable. And so you often get them in small billets. Yeah. And so trying to actually mill and mix these together, you end up deforming your metal, or it gets nasty. But I was thinking about our episode that we did on cryomilling with Cal Nano, and
Yep.
they actually
Came to
do
my mind.
quite a bit of they do quite a bit of work in this space because cryomilling allows them to take these down to cryogenic temperatures where things are a little more brittle. They can get much more homogeneous powders out of these and mixing. I'd reached out to Eric prior to this episode, and we were chatting a little bit about how they can, they have the setup and the throughput to actually make all sorts of HEAs and get like proper powders that are mechanically alloyed, essentially, before doing SPS. And I see SPS as being a really, useful way to start getting larger samples that can be tested for things like creep and other dynamic mechanical properties as well.
And by larger, remember a couple episodes we talked about, they can do large scale. They've pushed it even further. I just saw this week a post on LinkedIn where now they're doing 17-inch billets. I don't know if that's if they're circular or square, but still 17 inches. That is huge. We're talking like silicon wafer territory. That is really big.
Yeah, I mean, at that point, you're getting the desirable properties that you can get from the SPS, but now not only can you cut samples from it, you can start to machine useful parts out of that.
Yeah, you can scale.
Yeah, and I don't think anybody has the idea that HEAs are going to be large structural pieces, but for critical components that need a good mix of properties, right, you're now kind of in the range where you can get those SPS properties at those sizes. One thing I did see that was kind of interesting, I think one of these articles was a little bit dismayed, but another thought it was maybe a good thing, was a number of these metals, despite being in a unique alloy space, are still very similar to the alloys we know. And the methods of making them better through precise microstructure control, through precipitation hardening and such, are also very effective here. And so while not necessarily unique, we have the benefit of knowing a number of good strategies for making these better.
Yeah, we're not starting from like ground zero here.
Yeah, and a lot of the fabrication techniques also work, right? We talked about thermal spray on one of our old episodes, and there's plenty of articles of people using thermal spray to make HEA coatings already. And it's actually quite nice that these fit in with a lot of the existing technological methods, because if it required totally different technology, you could see adoption being a lot slower.
So we have the birth of an entire new class of materials. That doesn't happen every day. It happened in our lifetime. That's pretty exciting, right? And yet we haven't seen these. I don't think I own anything that has an HEA in it, right? We will follow up in a future episode and figure out what will it take for these things to make it to market. What will those markets look like? I'm actually really excited to learn more about those because I'm anxious to see where we can leverage some of these remarkable properties that are already starting to turn up.
Yeah, that's right. I think, taking a cursory glance to the literature, one of the things that's really exciting is that because you have so many elements and so much more space to explore, right, the degrees of freedom is much higher. We're seeing a lot of multifunctional materials emerge as a result, things that just wouldn't be possible in conventional steel families and such, things involving maybe their thermal properties, their magnetic properties that are really quite interesting and fascinating. And then when you expand this even further, we now have things like high-entropy ceramics. There's a huge world to cover, and I think we're really excited to do a follow-up episode where we dive a little bit more into how these are being implemented and where they're showing up.
Okay. Well, awesome episode. As always, huge props to our sponsors. We couldn't do it without you. American Elements. Go buy all the different metals you want. We gave you the whole periodic table as your palette, and they can provide it. So props to them. Great company. And Cal Nano, if you want to actually turn this into a part, you know that we love them. You know what they can do for you. Cal Nano's great stuff. And then obviously, we have a longtime sponsor relationship with Materials Today. We're super grateful for them. You know that they've been sponsoring us for several years now. So check out materialstoday.com. It's a great place to stay up to date with literature. We literally do it for every episode. They have great stuff in all areas of material science, including high-entropy alloys. You can check out also learn more about their journals, conferences, and other programs they've got going on.
As always, thank you for listening to this episode of the Materialism Podcast. If you have questions or feedback, please send us an email at materialism.podcast@gmail.com. It's really awesome, actually, hearing from people on there. It's probably one of the best parts of doing this. So if you like the show or you have feedback on the show, like, is there something we can do better? Reach out and let us know. Make sure you subscribe to the show on iTunes, Spotify. I don't think Google Play even does it anymore, but wherever you find your podcasts.
No, but now it's on YouTube. Now it goes straight to YouTube.
Okay, well, wherever you find your podcast, subscribe. and consider leaving us a review. It helps expose more people to the show and helps us improve.
And here's the real reason, it just makes my day. When I see a review, it friggin' makes my day. So we'd love to hear back from you.
Finally, you can check out our Instagram page at materialism.podcast, where we post artwork for the episode and give you a little sneak peek into what's coming up next. And finally, we'd like to give a shout out to Alphabot and Kolobyte for making the music for the podcast. They both do a ton of really cool synthwave music, so go check them out on Spotify and YouTube. Catch you next time.
See you later.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world, and are bound only by their imaginations in manipulating those materials.